Okay, so next we have Tom McDermott, N5EG, and he's going to be talking about the dual receiver RF module design for the Tangerine SDR. And Tom is also with the Tapper group. So go ahead, Tom.
All right, thank you very much, Nathaniel. Can you hear the audio okay?
It sounds great, thank you.
Oh, okay, very good. This presentation dives in a little bit deeper on the first receive module that Scotty talked about, which is a dual channel receiver. At HamSCI 2019 last year, there was a presentation on the requirements for the receiver, and at TangerineSDR.com there is a requirements document that discusses a little bit of the details. So if you have particular questions, you might want to look back to the videos that Jason, I think, has put up on HamSCI 2019, or look at TangerineSDR.com for documentation. So in this presentation, we'll give a little bit of a high-level diagram, which Scotty covered, on the receiver, an update of where we are on the receiver design at this point, a little bit of discussion on configurable settings for the receiver, and then some notes on characterization and calibration that we will plan to do for the receiver. This is a high-level diagram of the receiver. It's slightly unusual in the way that it's laid out, and we'll talk about that. This single module is a dual channel receiver, and as Scotty showed, there's room for 2 modules on the data engine, and so in fact possible to have a 4-channel receiver by putting 2 of these modules on one data engine. This module has a couple of SMA connectors for receive. The receive signal comes into a relay, and that relay either passes the signal into an attenuator or it selects a wideband noise source. Right now the noise source is set up to provide 5 dB excess noise ratio. That's 5 dB over the thermal noise. And that could be changed with some resistor value changes. Right now we think 5 dB ENR is probably the right amount. It then goes to a relay switched resistive attenuator, and then the optional pluggable filter that Scotty talked about. The entire RF section is isolated and ground from the digital and from the system ground. And there is a bonding strap, which is shown, I don't know if I have a mouse here. There's a bonding strap here in the center where if you choose, you can bond channel 1 analog ground to the digital ground, and the same thing on channel 2. If that ground is not bonded, then the channel 1 analog ground will float with respect to the system ground. Each of the channels then goes into a dual ADC driver, which is a 20 dB gain driver. The noise figure of the driver is spec'd at about 6.2 dB. And then that dual driver feeds a dual 14-bit analog to digital converter. And that ADC is clocked by a 122.88 megahertz signal from either the data engine or the clock module. There are some options to select where it's clocked from. And in return, it provides a double data rate interface to the data engine. There's enough bandwidth coming off a dual converter and enough pins that in general you need a DDR interface to the data engine. There's options to bond or to isolate the antenna ground from the digital ground. The noise source is relay switched. What all of that means is there are no active components ahead of the dual ADC driver chip, and so everything to the left of that transformer is passive, or in the case of the noise source, transformer coupled. And this is done in an attempt to preserve dynamic range and to keep spurious noise sources out of the front end. There is a passive pluggable filter option. We'll talk about that a little later. Right now we've designed an an AM broadcast band bandstop filter. Others could be designed, but we have that as the first design. There is an option for an active pluggable filter where we can pick up not only the RF connections, but also power and ground if in the future we want a active filter that has a preamp on it. There are no active components in front of the dual ADC unless we plug in an active pluggable filter, in which case there obviously would be. The attenuator is a relay switched attenuator selecting 0, 10, 20 or 30 dB attenuation modes. As of March 16th, we've completed the schematic. There's still a few tweaks. The layout of the engine of the RF module is very dependent on the exact details of the data engine. And so there's been a few pin swaps going on. So the schematic, I'll say, is complete, but we'll make a few tweaks depending on the requirements of the data engine. The printed circuit board layout is complete, but also being tweaked for dependencies on the data engine. And right now, this is down to a few pin swaps on the data side. Nothing has been fabricated or built yet. The future tasks we have on the receiver are to assemble the first prototype of the receiver units, to complete the data engine, to do checkout, to build a FPGA test firmware load so that we can talk to the analog to digital converter on the RF module, and to start acquiring test buffers. And the test software will retrieve test buffers, configure the ADC, and then we'll have to make measurements and start the characterization process for the receiver. We're anticipating that we'll have a layout spin or two on the receiver. There's almost always something that has to be modified or fixed on the receiver, since not only is it a digital device, but it's a very sensitive analog device at the same time. This is the preliminary layout of the dual channel receiver. It's 115 millimeters long. It's about 48 millimeters wide. The MEC connector that Scotty talked about is on the back side of this module. The back side is primarily two ground planes, the digital ground plane and the analog ground planes, one for channel 1 and a separate one for channel 2. And those are on the back side to try to shield this from the data engine signals. On the top side here, you can see the channel 1 antenna on the top left and the channel 2 antenna on the bottom left. Those go through the relays, and then in the center you'll see a pair of the filter modules, the plug-on filter modules. If you don't use a filter module, there's a bypass, and so you can put in a strap to bypass the filter module. If you equip a passive filter module, you just remove that strap and then plug on the filter module. And then goes through a U2 filter, which is a filter that is a roofing filter. It's a 55 megahertz low pass filter module. The spec says 40, but the roll off is pretty gentle. It then goes through a power and ground header. The active filter module will plug on to not only the filter input and output connectors, but also the power and ground connector. So the active filter module is larger than the passive, so that it can pick up the power and the ground connectors over here. Then there's a strap here if you want to bond the analog ground on channel 1 to the digital ground. You can plug on a 0.1 inch clip, and the same thing for channel 2, where you can plug on a shorting strap if you want to bound the two grounds. Then U6 is the dual converter. The dual low noise analog to digital converter driver chip, and then the dual channel ADC chip. There's a few power regulators to derive the low noise voltages for these circuits here. And then where the Tapper logo is, there's a lot of double data rate interfaces to the MEC 140 connector, which connects it down to the data engine. This is the layout of the AM broadcast band passive filter. You can see it's a fairly small module. It's about 10 by 20 millimeters in size. The active version of this will be longer, about 30 or so millimeters to pick up that power and ground connector. Modules can also be wider than 10 millimeters. The module widths can go up to about 20 or so millimeters if you have a particular filter that you need to design that takes more space. The width limit is due to the fact that we have, of course, to accommodate two of these, one for channel 1 and one for channel 2, and so we would need a pair of these. Getting a message, my internet connection is unstable here, so let me know if I have an audio problem. So in terms of configurable options, there's an option to bond or isolate the grounds. Isolated grounds help reduce common mode noise signals, and that can be very important in some applications. Some of the folks on the team have noticed a problem with common mode noise and have had to implement common mode noise chokes. Those come at the cost of a little bit of increase in attenuation. And so we've tried to provide a lot of common mode isolation on the receivers to avoid the need for common mode chokes. There may be severe cases where both are needed. If you use a powered remote external antenna, some antennas, for example, small powered loops or small powered dipoles may need power. And so I'll talk in the next slide or two about how to do that. Bonded grounds may be needed in some jurisdictions. There are some places where the input ground is required to be bonded, and so there is a bonding jumper for those particular applications. The noise source has a couple of options. There is a strap so that the noise source can be completely disabled and power removed from the noise source. I don't think that that'll be necessary, but there is a strap option to do that. If the noise source is strapped on, that is, power is applied, then the noise source can be turned on and off under computer control. So the noise source can be turned off and the relay connects the RF signal into the attenuators, the filters, and the low noise amp. Then the computer can turn on the noise source independently on the two channels, channel 1 and channel 2. That disconnects the receive signal and instead connects the 5 dB excess noise ratio signal to the attenuator. One would probably want the attenuator set in the 0 dB setting at that point. And this allows switching back and forth between the receive signal and the noise source, which will allow, for example, looking and trying to measure the background noise level. That's called a Dickey switch, where you can rapidly switch between those two. It also provides a way to calibrate the receive amplitude settings by looking at the broadband noise source and looking at the signal level from that compared to what's expected. So it provides a couple of different functions. In a lot of cases, we anticipate that folks will want to use a powered antenna. And so if you want to have a case where the receive ground is isolated and yet DC power is applied to the antenna, then one would probably hook it up like this, where the receive channel has its ground bonding disconnected so that its ground is isolated from the system. You would then power the antenna through a common mode choke so that you can have a DC power ground reference. You then need to have a bias T, which provides the differential mode choking so that you don't short out the receive antenna signal, and then a DC power. So this is how you would provide power remotely to a powered antenna, while yet maintaining an isolated receiver system. And again, if code requirements are that you bond this, then you can bond the ground, and you'll have to provide a second common mode isolation choke. So we've tried to provide a lot of flexibility in how the receiver can be connected. This is a simulation of the AM broadcast band passive bandstop filter. It's optional. The attenuation is in blue here on the left, and you can see that it notches out over a pretty wide frequency range. The AM signal, broadcast band signal, it's a reflective filter, which is shown at turn loss in red here. One of the issues with any kind of reflective filter is that there is a lot of group delay. And so here we can see two large group delay spikes at about 500 kilohertz and about 1.5 to 2 megahertz. And so if you equip this filter, then there will be a substantial phase nonlinearity in the AM broadcast band. In terms of characterization and calibration, we know we need design characterization, and what we mean by characterization is those RF parameters we think are likely to be similar across a wide production range of units. So that would be things like the noise source level from the onboard noise source, the frequency response of the noise source, the sensitivity and noise figure of the receiver, the frequency response of the receiver, the phase response of the receiver, channel isolation, phase noise, spurious responses, other things associated with the receiver, and the receiver channel group delay, which is primarily due to the 40 megahertz, very soft band limiting filter on the front end. Per channel calibration, where we anticipate likely significant differences between units, are primarily related to the filter group delay of the pluggable filter, and that group delay is orders of magnitude larger than the 40 megahertz band limiting filter. And so if we need precise group delay measurements and we need an AM broadcast band filter, then likely that will have to be calibrated on a per filter basis. Independently removed by either the data engine or the host software will be group delay. And in the case of multi-channel interferometry or polarization discrimination, if we've equipped, for example, a broadcast band filter, then the data engine is going to have to subtract out that group delay. And so also noise source level and frequency response may have to be slightly calibrated by the data engine. We're hopeful that with no optional plug-in passive filter, that the amount of group delay variation will be fairly small. One of the objectives of the receiver is to provide the capability for interferometry. And to do that, there's a couple of considerations we need to take into account. That the numerically controlled oscillators on separated receivers, these may be receivers separated by 10, 20, or 50, or 100 kilometers. Those NCOs need a common time and frequency reference for interferometry. The quality of that reference needs to be agreed upon by the science community. John Ackerman, N8UR, will talk about that in the next talk. The down conversion oscillators on separated receivers will have a static phase difference. That is, when you start the oscillator, its phase will be different than an oscillator on another unit. And so the phase offset will jump whenever that NCO is reprogrammed. So the static phase offset of that oscillator will need to be taken into account when doing interferometry. We may need compensation for things like RF filter component tolerance, antenna cable length differences, antenna preamp differences if we use an active receive antenna, antenna phase center differences, things like that. Wideband measurements may incur phase dispersion in some cases. Not using an AM broadcast band filter is desirable for wideband measurements. An active receive antenna may present some complications. There is a 3 antenna closure phase method called self-calibration that can be used to compensate for static phase differences at multiple antennas, and the references for those are here. And I think we're about out of time, so are there any questions?
Thank you very much, Tom. Yes, moderators. Bill, are there any questions?
Oh, but I don't know if we have time for them. But one of the questions is, how good is the reliability of the relay switches, particular temperature range? Like if we use this very high up north, below zero temperatures.
Yes, we have not looked at the temperature reliability of the relays. The relays are specified as 1 million cycles, and so they should have a fairly long reliability. I'm not aware too much of the temperature limitations. I think there are other temperature limitations in the entire package related to capacitors. There are electrolytic capacitors all over the data engine and RF receivers, and I think those will have their own temperature limitations of around 0 to -20°C. So in extremely cold locations, it may be required to put the data engine and RF receiver module in a heated enclosure.
Thank you very much, Tom. Okay,